We will now use the concepts of circular motion to solve problems. Let's start with this problem. The moon revolves around the earth in 29 days in a nearly circular orbit with a radius of 3.8 times 10 to the power 5 kilometer. Assume that the motion of the moon is uniform, which means its speed is uniform. With what acceleration is it falling towards the earth? What is its centripetal acceleration? Well, we have the data and you know the equation for the centripetal acceleration. Do you know? What is the equation for centripetal acceleration? A equal to v squared over r, but we don't know v, the linear speed. We only know the period. Well, the time taken for one revolution is 29.5 days. We know the period. Alright, if we know the period, can you use that to find a useful value? Yes, if you know the period, we can find the angular velocity. Alright, now what is the equation for the centripetal acceleration in terms of the angular velocity? A equal to r omega squared. So, we will first obtain the angular velocity using the period. The period is 29.5 days. Convert that to seconds. That is 2.5 times 10 to the power 6 seconds. And the radius is 3.8 times 10 to the 5 kilometer. Convert that to meters. 3.8 times 10 to the 8 meter. Those are the data we know. Using the period t, we obtain the angular velocity omega. Alright, how do we obtain the angular velocity omega if you know the period? Omega equal to the angle described during one period is 2 pi. So omega equal to 2 pi divided by the period. That will be 2 pi divided by 2.5 times 10 to the 6 seconds. And that is 2.5 times 10 to the negative 6 radian per second. Is that right? That doesn't look right. Okay? Do you want to check it on your calculator and make sure this is right? Omega equal to 2.5 times 10 to the negative 6 radian per second. Well, once you know omega, we can calculate the centripetal acceleration equal to r omega squared. We know the radius, we now know omega. Therefore, the centripetal acceleration is r times omega squared, and that will be 0.0024 meter per second squared. Well, that's the earth, that's the moon. The moon goes around the earth and the centripetal acceleration is 0.0024 meter per second squared. Now tell me, the moon is falling towards the earth with this acceleration. Why doesn't it then fall down to the earth? Why is it then keeping going round in a circle? Now, if you notice, the surface of the earth, I'm going to draw it over here. If this is the surface of the earth, as the moon has two types of motion. It has a linear motion and it has a motion towards the earth. Now what happens is, as the moon goes away, it also is falling. Now look at the amount of fall. The amount of fall during this time is this: the moon has actually fallen that much. But during that time, the surface of the earth also has fallen by the same distance, because the earth is spherical. That means the amount of fall of the moon and the amount of fall of the earth. See, if you now look at that position, this is the fall of the earth. So the moon has fallen by this distance, the surface of the earth has fallen by the same distance. It means the moon will be always at the same height. It will keep going in an orbit. Okay, so the moon is actually falling towards the earth at this constant acceleration. Alright, let's do another problem. In the absence of this acceleration, you know that the moon will simply go away along the tangent. An electrically charged particle can travel in a circle of uniform magnetic field. An electron is observed to take a circular orbit with a radius of 30 centimeters, traveling at a speed of 100 meters per second. What is the centripetal force acting on the electron in this circular orbit? How much work is done by this force in 2 electron revolutions? Well, first of all, we need to find the centripetal force. Now, what is the equation for centripetal force? Centripetal force is mv squared over r. So all we need to find the centripetal force, we need to know the mass of the electron. It is a constant value that is available in many tables. I think it is 9.1 times 10 to the negative 31 kilogram, right? You want to check it? It's available in all tables. So, once you know the mass of the electron, you know its speed, and do you know the radius? The radius is 30 centimeters. Therefore, we can find the centripetal force. Radius is 0.3 meter. The speed of the electron is 100 meters per second. And the mass of the electron is 9.11 times 10 to the negative 31 kilogram. So this is all we need to find the centripetal force. The centripetal acceleration, the centripetal acceleration is v squared over r. That is 100 squared over 0.3. 3.3 times 10 to the 4 meter per second squared. And the centripetal force will be mass times acceleration, mv squared over r. So multiply the mass of the electron by its acceleration, and that gives you 3 times 10 to the negative 26 Newton. It's a very small force that keeps the electron in that circular orbit. How much work is done by this force in 2 electron revolutions? Now, we haven't actually discussed the concept of work to answer that question. But let me say this. A force does work when it produces displacement in the direction of the force. So, now, in this case, what is the direction in which the electron is moving? Now let me see if I can illustrate this here. The electron is moving in a circular path, and the direction of the force is towards the radius. Now the electron is moving at any instant at right angles to the force. So if this is the direction of the force, there you are. Now, at any instant, the direction of displacement is exactly perpendicular to the direction of the force. That means there is no displacement in the direction of the force. If there is no displacement in the direction of the force, then that force is not doing any work. So the centripetal force is not really doing any work on the electron because there is no displacement produced in the direction of that displacement. Okay, let's move on. Well, what is the answer for this? What is the work done? Centripetal force always acts at right angles to the direction of motion. That means there is no displacement in the direction of the force, and therefore the work done in this case is 0. Alright, let's do another problem. A car enters a circular curve of curvature, radius of curvature 0.4 kilometer at a constant speed of 83 kilometer per hour. If the friction between the road and the tires can support a centripetal acceleration of 1.25 meter per second squared. Now, in other words, that is the safest acceleration that the car can have. If the speed increases above this, the car will not be able to keep in that circular track. That is the meaning of that. Now, does the car negotiate the curve smoothly? Well, I think I need to change my argument a bit. Our aim is to find if this speed is a safe speed. Now, how do you know if that is a safe speed? Well, this is the maximum centripetal acceleration that the friction between the road and the tires can provide. You see, the frictional force cannot exceed this value, and therefore we need to find out if this speed is a safe speed for that centripetal acceleration. Alright, well, this is the speed of the car, that is 23.1 meter per second, and the centripetal acceleration that will be allowed by the force of friction. This is the safest centripetal acceleration, that is 1.25 meter per second squared. What is the equation for the centripetal acceleration? Centripetal acceleration is v squared over r. We know the radius, we are given the centripetal acceleration, therefore we can calculate the safe speed for that radius of curvature, and that's what we're going to do. So the radius of curvature of the curve is 400 meters. When the car negotiates a turn, it is the friction between the tires and the road that supplies the necessary centripetal force. Now, if v is the maximum safe speed for this curvature r, then the centripetal acceleration is v squared over r, where v is the safe speed for that particular curve. Therefore, v squared is the acceleration multiplied by the radius. The acceleration is 1.25 and the radius is 400 meters. And that is 500 meter per second squared. That is v squared. Therefore, what is v? V is 22.4 meter per second. It means the friction between the road and the tires will allow a maximum centripetal acceleration of 1.25 meter per second squared for this particular radius. And that means you can drive up to 22.4 meter per second safely on that curve. And what is the speed at the time? 23.1. Is this a safe speed? No, this is above the allowed safe speed. So you can actually be thrown away, or you can skid, and that can be dangerous. Is that right? Now, every time you see a curve, you see a speed limit there. You are not allowed to go above that speed. That is the maximum safe speed for that curve. If you exceed that speed, you are then asking for a greater centripetal acceleration, which may not be there. And if it is not there, you will not get the centripetal force to keep you in that circular track. So you will be thrown away from that circle. Since the actual speed of the car is greater than the safe speed, the car does not negotiate the curve smoothly. That is where you hear the screeching and howling of the car tire with the road. Okay, let's look at another problem. A 100-gram disc sits on a horizontally rotating turntable. The turntable makes 1 revolution each second. The disc is located 10 centimeters from the axis of rotation of the turntable. What is the frictional force acting on the disc? The disc will slide off the turntable if it is located at a distance larger than 16 centimeters from the axis of rotation. What is the coefficient of static friction? Well, this is a good problem. I want to think about this and see what are the given information and how we use the given information to solve this problem. Now, here I have the turntable. The turntable can be turned, and I'm going to place this disc on the turntable. Alright, now when the turntable turns, the disc is going in a circle. Now tell me, what is it that provides the centripetal force for it to go in a circle? And it fell off. Why did it fall off? Now, the centripetal force is provided by the friction, and the friction between these two is not increasing. If I increase the speed, you can see when the speed is small, it will not fall off. So the centripetal force mv squared by r is only small. You need only a small centripetal force now. But if I increase the speed, there you are, it's fallen off. Well, so in this case, we can figure out the centripetal force, which is the friction between the disc and the turntable. And the centripetal force, mv squared by r, is that frictional force. Is that right? And that is what we're going to use in solving this problem. What is the frictional force acting on the disc? The frictional force is the centripetal force. Alright, this is the disc which is rotating, and we place, well, this is the turntable, and we place a disc of mass m equal to 0.1 kilogram on the turntable, and the radius, the distance of the disc from the center of the turntable is 0.1 meter. So when the turntable goes around, this disc will rotate in a circle of radius 0.1 meter. So the turntable makes 1 revolution each second, means that it describes an angle of 2 pi radians in 1 second. That means that is the angular velocity. Is that right? If it goes around once in 1 second, 1 revolution in 1 second is 2 pi radians per second. That is the angular velocity. So omega equal to 2 pi radians per second. Can you calculate the centripetal force? The centripetal force, therefore, is F centripetal is mr omega squared, mass times centripetal acceleration. We have shown that the centripetal acceleration is r omega squared. Therefore, the centripetal force is mr omega squared. We know the mass, we know the radius, we know omega. Therefore, the centripetal force is 0.4 Newton. In order for that disk to sit there and go around the circle comfortably, there must be a minimum force of 0.4 Newton. In the absence of this centripetal force, the disk will move away towards the tangent. And where does the centripetal force come from? It comes from the friction between the disk and the turntable. Well, so that is the frictional force. In the B part, the disk will slide off the turntable if it is located at a radius larger than 16 centimeter. That means if you move the disk away from the center, the radius is increasing. Is that right? That's right. So what happens to the centripetal force? Well, the maximum frictional force on the disk when it is 16 centimeter from the center of the table is again mr omega squared, where the radius is now 0.16, and that will be 0.63 Newton. So that 0.163 Newton is the maximum centripetal force. What does that mean? Well, if the disk slides away at that radius, that means that is the maximum frictional force the disk and the turntable can provide. The frictional force cannot increase more than that. That means this 0.63 Newton is the force of limiting friction. And what is the normal force in that case? What is the force pressing the disk onto the turntable? The force pressing the disk onto the turntable is its weight. Now, its mass is 0.1 kilogram. Therefore, its weight will be 0.1 times 9.8, which is 0.98 Newton. So, we have now two important quantities. What are they? We now know that the maximum frictional force between the disk and the turntable is 0.63 Newton. And that is the force of limiting friction. And we know the normal force pressing the two surfaces together. If you know these two quantities, can you calculate the coefficient of static friction? The coefficient of static friction is the force of limiting friction divided by the normal force, or the force of limiting friction is mu s times Fn, or mu s equal to Fs over Fn. That will be 0.64. Alright? Okay, let's now talk about another concept called drag forces. Now, drag force is a kind of frictional force. When I drop this eraser in air, as the eraser keeps falling, it is falling through air. That means it has to overcome a resistance. It has to push away the air to go through it. That is a drag force. When you want to swim in water, isn't it difficult for you to swim? Why? Because you need to take the water apart and go and occupy the space water has been occupying. You need to overcome a resistance. Well, the resistance becomes very obvious if you drop a piece of paper. Is that right? When you drop a piece of paper, it takes a long time to fall. Have you ever tried that? Now, when I allow this paper to fall Well, you can actually see it takes a little while to fall. There you are. Now, why does it take that long? On the other hand, this eraser falls pretty fast. Well, there is a drag force preventing the paper from falling. Now, what does the drag force actually depend on? As an object keeps falling, its speed increases. As the speed increases, the drag force also will increase. So in many cases, drag force depends on the speed. Now, if you take a can of engine oil and put it in a transparent container and you drop an iron ball into it, it is very interesting to watch it. As it keeps falling, it will reach a uniform velocity. It will stop accelerating. As it keeps falling, its velocity increases, and as the velocity increases, the drag force also increases. As a result, after some time, the weight of the ball acting downward will be balanced by the drag force. And from that time on, there will be no net force on that object. Well, when an object moves in a medium such as air or water, it experiences a drag force opposite to the direction of motion, which reduces its speed. The drag force increases with the speed of the object. You know, when you swim slowly, the resistance is not as much as when you want to swim fast. The speed increases, the resistance also increases. Now consider an object falling freely. Now what are the forces acting on it? Its weight mg is acting vertically down, and the drag force will be acting vertically up. As the velocity of the object increases, what happens as the velocity of the fall increases, the drag force will also increase. Until a time will come when the weight is equal to the drag force. Now, at this stage, there will be no net force acting on the object. So, if you jump from a very big height, as you keep increasing your speed, the resistance of fall will also increase. A time will come when your weight acting downward will be exactly equal to the drag force, and at that time there is no net force on you. That means there will be no more acceleration. You will keep falling with the same speed. You see that? It's a very interesting phenomenon. Now, from this time on, the object will fall with a constant velocity, and this constant velocity is called the terminal velocity. Now, some objects, you see, this paper takes a very long time because the paper reaches the terminal velocity very fast. You can see it falls almost with the uniform speed, whereas the eraser takes a long time to reach the terminal speed. If you want this to reach the terminal speed, you need to drop it from a big height. Well, have you ever gone on skydiving? You can experience that terminal speed if you go skydiving. Now, here is the illustration of somebody skydiving. Now, the moment you jump out, there is only one force on you. You see? At the time you jump out, there is only one force on you, and that is your weight. Now, suppose this man has a weight of 100 Newton. He's a fairly heavy man. Now, with time, he will increase his speed. As the speed increases, the drag force will increase. So soon the drag force becomes, say, 400 Newton. What is the net force on him now? The net force is only 600 Newton. That means he's not falling as fast as he did first. Because the net force is now small, the acceleration is small. But he's still increasing his speed. Because he is increasing his speed, the drag force will now increase. Now, a time will come when the drag force and the weight are exactly equal. The weight is 1000 Newton, the drag force also is 1000 Newton. The forces on the skydiver are now balanced. That means from that time on, the skydiver will be falling with a uniform speed, and that is his terminal speed. Any object that is dropped from a sufficiently great height will eventually achieve terminal speed. Let's do a small problem. A skydiver of mass 60 kilogram can slow herself to a constant speed of 90 km per hour by adjusting her form. What is the magnitude of the upward drag force on the skydiver? Well, at the time the skydiver achieves that uniform speed, uniform constant speed, her weight is balanced by the upward drag force. That is the one we use to do that problem. Alright, let's do that. Now here's the skydiver. Well, I got a poor picture for her, but I think you will excuse me for that. The diver is falling with a terminal speed of 90 km per hour. Now, there is no net force on the diver at that time. When the speed is the terminal speed, there is no net force. That means the weight acting on her, what is her weight? Mass times acceleration due to gravity, that is 588 Newton is acting vertically down. And the drag force will therefore be acting up and exactly equal to 588 Newton. Therefore, the upward drag force on her will be 588 Newton. There you are. Alright, now the second part is if the drag force is equal to bv squared. What does that mean? In this case, the drag force is proportional to the square of the velocity. That means as the velocity increases, the drag force will increase not linearly, but according to the square of the velocity. So we should be now able to say this drag force, which drag force? This 588 Newton equal to bv squared, where v is that terminal speed and b is the constant of proportionality. And we are required to find that's the value of that. So v equal to 90 km per hour, that is 25 meter per second. Therefore, we can say 588 Newton equal to b times v squared, 25 meter per second squared, or b equal to 588 divided by v squared, that is 0.94 kilogram per meter, and that is the value of b. Okay, another problem. A similar one. A small pollution particle settles towards the earth. What is a pollution particle? Now, if you look, most of us say, oh, our living room, our house is so clean, there is no dust in our room. But if there is a light coming into your room through a hole, look into the path of that light in your living room. There will be so many dust particles. You see, dust is roaming around all over. In fact, when I look at the light of the projector, I can see a lot of dust particles there. That's a pollution particle. And that pollution particle, very often, because it is so small, they will reach terminal speed very fast. So as it moves down with the terminal speed. That's what this problem is talking about. A small pollution particle settles towards the earth in still air with a terminal speed of 0.3 millimeter per second, very slowly. The drag force on the particle is 10 to the power of, well, the mass of that particle is 10 to the power of -10 gram. And the retarding force is of the form B times V. Retarding force is of the form B times V, means retarding force or the drag force equal to BV. What is the value of B? The same problem that we did before. We can find the drag force. We first find the drag force. How do we find the drag force? Because the pollution particle is moving with the terminal speed, the drag force opposing motion equal to the weight of the pollution particle. Well, we know the mass of the particle, therefore we can find its weight. Mass is 10 to the power of -10 gram. You need to convert that to kilogram. 10 to the power of -13 kilogram. The terminal velocity V sub t is 0.3 meter per second. Is that 0.3 meter per second? No, 0.3 millimeter per second. I meant to write millimeter here. And convert that to meter. That would be 3 times 10 to the -4 meter per second. This is 0.3 millimeter per second, which is 3 times 10 to the -4 meter per second. Now, can you see the pollution particle I have just drawn here? The weight is 9.8 times 10 to the -13 Newton. And when it is in terminal speed, the drag force will be acting upward and will be exactly equal to the weight. And we are told that the drag force is of the form BV. So mg, the weight of the pollution particle, is the same as the drag force BV. So solving for V gives you B equal to mg over V sub t. M is this, and V is given to us, which is, yes, this one, 3 times 10 to the -4. So mg, 10 to the -13 times 9.8 over 3 times 10 to the -4, and that is 3.3 times 10 to the -9 kilogram per second. That is the value of B. Okay, these are very simple problems. Let's try one more problem. A 0.2 kilogram stone attached to a 0.8 meter long string is rotated in the horizontal plane. The string makes an angle of 20 degrees with the horizontal. Determine the speed of the stone. Now, what is the meaning that a stone tied to a string is rotated in a horizontal plane? Let me see if I can show that to you. Now, in place of the stone, I have the metal ball, and this is the length of that string. And you can see it is made to go around a circle in a horizontal plane. This is what the problem says. Now, at any instant, let's stop this at any given instant here, for example. That means the string is now inclined at an angle with the vertical. If this is the vertical, when the string is like this, it has a certain angle at any given time. Is that right? Yes. Now, if the speed is increased, that angle will increase. See what happens? I'm increasing the speed, that angle is changing. Angle is increasing, if you notice that. So, if I decrease the speed, I'm decreasing the speed, and the angle is decreasing. So what is it that we need to find? Well, we need to determine the speed of the stone when the angle is 20 degrees. The string makes an angle of 20 degrees with the horizontal, and determine its speed. In other words, when the string makes an angle of 20 degrees with the vertical, what is its speed? Alright, let's see how we can set it up. Now I have drawn two diagrams here. This one is the stone going in a circle. Remember that horizontal circle? And this is the vertical position, and this is the position at any given time, and the angle given to us, what is the 20 degrees? 20 degrees with the horizontal, not with the vertical. This is 20 degrees. Now, if that angle is 20 degrees, what will be this angle? If I draw a line from the center to the stone, remember that will be at right angles to this line. You must understand that if this is the vertical position and the stone is over here now, this distance is, well, when this is at right angles, I have that diagram here, then that angle will be 20 degrees. There you are. Okay. So the length of the string is 0.8 meter. So this is the length of the string, which is the same as this, which is 0.8 meter. Theta is 20 degrees. The angle made by the string with the horizontal is 20 degrees. Now what I have drawn, this triangle is, this is the vertical, this is the length of the string, and I drew the line perpendicular here. See a line drawn perpendicular from the position of the stone to the vertical, and it is that line. And let me draw that over here. It is this line that I have drawn there, and that angle will be 20 degrees. So you can see that angle and this angle are the same. It is this triangle that I have drawn here. And let's see, the mass of the stone is 0.2 kilogram. The radius r of the circle, what is the radius r of the circle? This is the radius r of the circle. The radius r of the circle can be written in terms of this length L. If you look at this triangle, you know that cosine of 20 degrees is adjacent side divided by hypotenuse. Therefore, this adjacent side, which is the radius, equal to the hypotenuse times cos 20 degrees. So we can write R equal to L cos 20 degrees, and that is 0.75 meter. The radius of that, the radius of the circle, the horizontal circle, is 0.75 meter. Now, the tension on the string T has a vertical component. You can see the force when the pendulum goes round, the tension on the string is directed like this. It has a vertical component and a horizontal component. Now, it is the horizontal component that supplies the centripetal force. In order to keep that stone in a circle, going around a circle, you need the centripetal force. Now, where is the centripetal force going to come from? The centripetal force is actually provided by the horizontal component of this. Now, if you look at this, this angle will be 20 degrees. Therefore, well, no, that angle won't be 20 degrees. We already said it is this angle that will be 20 degrees, which is this. So if this angle is 20 degrees, this will be 20 degrees. And therefore, the component towards the center, the horizontal component, will be t times cos 20 degrees. And the vertical component will be t times sine 20 degrees. And it is this component that provides the centripetal force to keep that stone in circular motion. Okay. So t sine 20 degrees, what does that do? What is the function of that t sine 20 degrees? This t sine 20 degrees balances the weight of the stone. So we have t sine 20 degrees equal to mg, the weight of the stone, which is 1.96. So we have one equation, t sine 20 degrees equal to 1.96. What about this? The t cos 20 degrees provides the centripetal force, and the centripetal force is mv squared over r. So t cos 20 degrees is mv squared over r, but m equal to 0.2 kilogram, the radius equal to 0.75 meter. Therefore, t cos 20 degrees is 0.2 v squared divided by 0.75. Now, if you divide the first equation by the second equation, what does that give you? Divide 1 by 2. T sine 20 divided by t cos 20. What does that give you? T sine 20 divided by t cos 20. The t's will cancel. That will give you sine 20 divided by cos 20 is tan 20. And on the right side of the first equation is 1.96. The right side of the second equation is 0.2 v squared over 0.75. And let me do that for you. So what I have done there is the left hand side of the first equation is t sine 20 degrees equal to 1.96 is the first equation. T cos 20 degrees is 0.2 v squared over 0.75 is the second equation. Divide the left hand side of the first equation by the left hand side of the second equation. Divide the right hand side by the right hand side. Now, there t and t goes. Sine 20 divided by cos 20 is tan 20. And here, when you want to divide a number divided by a fraction, you know that this 0.75 will go up. That will be tan 20 equal to 1.96 multiplied by 0.75, and this will stay on the denominator. That's how we got this one. Tan 20 equal to 1.6 times 0.75 divided by 0.2 v squared, and solve v squared from there, and that gives you 20.2, and therefore v equal to 4.5 meter per second. So when the string makes an angle 20 degrees with the horizontal, the speed of the stone is 20 meter per second. If you increase the speed, the angle will decrease. Okay, I think we have done enough number of problems in circular motion. We will revisit this in Unit 4 when we discuss rotational motion. All the terms we discussed here will be used in that section in rotational motion. Well, I'm going to stop this lesson. I think we have come to the conclusion of Unit 2. That means you must be getting ready for the test now. Unit 2 test. And make sure that you understand the practice test. You can do all the questions. And when you have done that, then go and do your test. And make sure you keep to the schedule. Do not lag behind. Always keep to the schedule. And the best thing is to always try to be ahead. Okay, I will get back to you with Unit 3 later on.